Hi, so can we explain statics just in a few minutes, right? Yes, I think we can. So statics, as the name suggests, everything is not moving, it's not dynamic, so there will be no acceleration, right? So in that situation, statics means acceleration will be 0. And now let's go back to thinking about our second law of Newton's law. So it's force summation of all the force, sigma F, is equal to mass times acceleration. Why do I add a sigma here? Because, for example, I have a truck right here, and that is on the ground. And so it's driving, it's having a pulling force. And then also there's going to be friction right here, opposite direction of pulling, so that's going to be summation. So if I use this F minus friction, that's going to be, I consider those multiple forces together, consider their magnitude, which is, for example, 10 Newton. That's the number of the force, the strength of the force. Also consider the direction. Is that going to the right or is going to the left, right? Okay, so that's summation of the forces equal to mass times acceleration. Now here, statics, what? Acceleration is 0. What does that mean? Then we come up with summation of all the forces equal to 0. That's statics. So think about another example. If I have a block here, and I have force F1, and I have a force F2, the opposite direction, where do you kind of know? I mean, common sense. If F1 and F2 both are equal, for example, to 12 Newton, what happened to the block? Block is going to be static. It's not moving. In other words, we can see it is at equilibrium. The force is at equilibrium. It's balanced up each other. So when summation of forces equal to 0, we have equilibrium equal to 0. Then now let's consider the force. We're going to start drawing a Cartesian coordinate, x and y and z. So we have three-dimensional. X is horizontal direction and y is vertical and z is front and backwards motion. So when we are thinking about object at a 3D space, for example, I have a object here in 3D, and this object could be subjected to many forces. And however, if we say this object is at equilibrium, we can say the forces at x direction of them together have to be what? Equal to 0. So in other words, all those multiple forces, if you are going to decompose each one of them at x, y, z direction, and you add all those decomposed component x direction together, they add up together, consider their magnitude, consider their direction, left and right for x, they're gonna sum up equal to 0. And the same thing, if you're going to consider all the y direction component of all those forces, they have to be equal to 0, right? If not, what happened? It's going to move that direction because acceleration here is no longer 0, then you will have force in that direction. When you have a force, you're going to have a direction. You're going to have moving, no longer static. So now also we have forces at z direction equal to 0. So from that governing equation, we come up with three sub-equations for x and y and z. Okay, so we have three equations here so far. Now let's consider also, when we have a movement of a subject in 3D, it doesn't have to be translational. What I mean translational means they are just moving. Like, For example, in space, x direction or y direction or z direction or combination of them, like moving at xy direction, going to the right and also going to the top, right? But here we're talking about another type of movement. In addition to translation, we're going to call rotation. If it's rotation, for example, I have a object and that is spinning around this x-axis. So it's just spinning around it. Same thing, I might have something that's spinning around the y direction or something spinning around z direction. Or it can be spinning around any axis in space. For example, something around here, spinning around that axis. So in that situation, we're going to be talking about rotational movement. Now we go back to our Newton's second law. We said the summation of forces equal to mass times acceleration. That's for translation. When the force is making a move translational direction. But how about rotation? Do we have an equation for that? Yes, we do. It's going to be summation of moment. This m means moment, also called torque, right? And that's going to be the driving reason behind to make this object rotate. Thinking about when you open the door, that door rotating around that hinge, right? And that is a rotation movement. And how do you open the door? Because you push around it. You create that moment, creating that torque. Like the same thing when you're trying to tighten up the nuts using the wrench. You go around clockwise to tighten, right? So you making that moment to make that rotational movement. So then what would be the equivalent for mass here? It's going to be I. So what is our I here? I is going to be our mass moment of inertia. Well, why the m here and I here is equivalent, in translation and the rotational world. Think about it. If you have a truck and then you have like a feather right here. You're trying to move them, make them translational movement. Which one would be easier? No doubt, right? This is easy to move the feather. Why? Because the mass of the truck is the resistance to your translation. So that creates a resistance to the translation. So that's important, resistance. So in another word, what will be the resistance for rotation? Then that's your I here. Resistance to rotation is going to be moment of inertia, mass moment of inertia. And here, a quick review, what's going to be mass moment of inertia? That's going to be in a unit of mass, kilogram, times distance square. So it's going to be kilogram meter square. That's mass moment of inertia. Okay. Now, let's look at this third term, acceleration. Acceleration is in translation. So how do you explain the acceleration in rotational world? We learned in freshman engineering it's going to be what? Alpha. So what do we call alpha? It's going to be angular acceleration. So angular acceleration, now let's discuss about the unit. Let's review acceleration unit. Acceleration is what? Meter per second square, because it's a change in velocity over time. Meter per second divided by time, meter per second square. So what is going to be angular acceleration? What is going to be alpha? It's telling us when you're talking about angular, it's basically moving from here to here. You are talking about the angle. And so that's going to be radians. Describe the angle is flipped, divided by secant square, right? Because let's quickly review. Alpha is going to be the change in angle divided by time. That's going to be angular speed here. Then divided by time again. So that's going to be radians per second square. So knowing that, we have the equation for rotational world. M, the torque or the moment, is equal to I, mass moment of inertia, times alpha, angular acceleration. We can use dimension homogeneity trying to prove this equation again. So let's see. Summation M is equal to I alpha. Let's see, left and right side has the same dimension. M, we're talking about its torque, right? Torque, what's the unit for the torque? It's going to be force times moment of arm. That's going to be force times distance. So it's Newton times meter. So Newton times meter for the left-hand equation. Our I, mass moment of inertia, is mass times the distance square, so meter square. And alpha is going to be radians per second square. So now let's derive a little bit more. How about we just change meter, and then radians has no unit, right? Radians is dimensionless. Then we have meter per second square. So I'm actually get rid of the radians because it has no dimension. Now what's meter per second square? That's our acceleration. And what's mass? Kilogram times acceleration. Mass times acceleration. That's going to give us force, which is Newton times meter. So left side and right side does have the same unit. So that proves this equation. Why do we have to spend time on this equation? Remember, we are talking about rotation. In rotation, what causes rotation? You have to have a torque, the M. And what's the resistance to this rotation? It's going to be your mass moment of inertia, I. And what's being generated? It's going to be our angular acceleration. Well, our problem we're looking at is static. If it's static, will we have rotation? No, we will not have rotation, just like we will not have translation either. So in that situation, our alpha here is going to be equal to 0 because it is static problem. So because of this, what's this equation going to give us? Summation of all the moment, summation of all the torque is going to be equal to 0. So that's our second set of equation. Remember earlier we have summation of forces equal to 0. Now go back to our coordinate here. We're talking about in this coordinate rotation, we're going to have rotating around the x or around the z or around y, all of those, and or any arbitrary rotation around any axis in the space. But if you have arbitrary rotation, you can decompose this to x and y and z also. So in other words, if it is static, we're going to get another set of equation. Moment rotating about x axis will be equal to 0. Moment rotating about y will be equal to 0. Same y's moment about z will be equal to 0. That's going to be another 3 equations. Right? So that basically is statics, because you have earlier you have this equations as well, or the forces, and now you have moment, all of them. So total gonna give you 6 equations. That's the essence of statics, because at the end you're going to look at a structure no matter what. You're gonna be looking at, if it's static, it has to have satisfy all those 6 equations. Then in that situation, you can solve your statics problem. So have to start thinking about how do we solve unknowns in 6 equations, right? But that's the essence of statics. All right, that's statics explained in few minutes. Well, 15 minutes. All right, bye now.